Excuse me. Note to self, only karaoke after your talk. Okay. So Sebastian Pineda, I want to thank the organizers for this opportunity. And so I'm a research scientist at the University of Colorado and the Laboratory for Atmospheric and Space Physics. So me and my group have been really working towards really understanding and developing what we know for magnetic star-planet interactions. So I'm presenting today the case of YZ SETI. Really on behalf of our group here and the collaborators listed there. It's been really a team effort, so take it away. Okay, so I want to begin with kind of recapping why we think there may be star-planet interactions occurring in this particular system, YZ SETI, and then go on to our ongoing work using the magnetic field topology to kind of probe that possibility and see if the story still holds together. So if you're not familiar with YZ SETI, it's a low-mass M dwarf. It's host to 3 likely Earth-mass planets in a really compact configuration. So before we kind of get into the particulars of that system, why are we actually interested in searching for magnetic star-planet interactions? And what that means is that there's a physical connection between the host star and maybe close-in planets, mediated by the stellar magnetic field. Okay, maybe that's interesting, but really, what it allows us to do, if we can clearly demonstrate that these processes are taking place and confirm that these interactions are really happening, that they're detectable, then we can use that as a tool to potentially probe the magnetic field properties of the planets, since the strength of that interaction strongly depends on the magnetic properties of the planets. But really for this stellar audience, and really I'm a stellar astrophysicist, the interactions are really actually really unique probes of the stellar physics. The wind properties are really important for the interaction itself. And this may be one of the few ways we can test that kind of physics throughout the stellar magnetospheric spheres and at different points throughout that space. Okay, so what are we talking about here? I'm going to focus on the Soboff-Feinick regime. What does that mean? Well, the idea is that when you have these close-in planets, they're interacting with the stellar magnetic field, they're perturbing that field, and that perturbation is stronger when the planets are more magnetized. The idea is that the perturbation travels along in these oscillations along the magnetic field line back to the host star. And those waves, through wave-particle interactions, energizes the plasma near the stellar surface, and that produces potentially powerful and strongly beamed radio emission. So one of the things I want to emphasize at this point is that the geometry is really important because the radio emissions are anisotropic. So they're actually beamed through these cones that are at large angles with respect to the direction of the local magnetic field at the source. So it's possible that we may not be seeing them depending on the geometry. So keep that in mind. Now I'll focus on the Soboff-Feinick regime because it is in this regime where the radio emission frequencies are dictated by the strength of the stellar magnetic field, which means that they're often at larger frequencies and more readily detectable by our most sensitive radio instruments. So that was the idea, and one of the things that we began looking for. So I'm going to show these results in a moment. With regard to YZ SETI, but it's part of a broader program looking at multiple exoplanet hosts. And Jackie presented a poster on this earlier, and please talk to her if you want to hear more about our broader survey. I'm going to talk about YZ SETI here in particular. So what I'm showing here now is the radio light curve in Stokes V in just the circularly polarized light from our paper last year. So in this first epoch in blue, this is highly circularly polarized burst that we saw. We also saw in a subsequent epoch in orange, this other shorter burst. Now, in the blue light curve, here on the stuff on the right, is actually the beginning of a larger flare, which is almost invisible in the Stokes V circularly polarized light. There's actually a huge Stokes I flare that happens right there. And this thing is actually probably something maybe akin to a type 3 burst. But that doesn't matter because we're actually interested in these polarized bursts. And when we actually looked at the phasing in orbital phase with respect to the innermost planet, YZ steady b, we saw this interesting coincidence that this burst kind of lined up with this broader burst. The alignment's not great, and their morphologies are kind of different. But not long after our reported detection was published, Trujillo showed that in their GMRT observations, they also had circularly polarized bursts, also at similar phases that our initial burst detections took place. Now, the polarization of the radio emission is exactly what you'd expect from potential ECM bursts associated with star-planet interactions. This is the kind of thing we're looking for, and to see it recur multiple times at similar orbital phases was really, really interesting. So let's take a broader view here. So I'm showing here now is a way to kind of visualize the literature radio data sets. So this is meant to represent the orbital position of the innermost planet, and then these arcs describe the radio epochs and whether we have detections or non-detections, et cetera. So in black are the unpolarized radio detections. In gray showed the orbital phases corresponding to our non-detections. And over here in these colors are our polarized radio detections. So for example, in this longer epoch, we had consistent unpolarized radio emission throughout that 6-hour observation. And then multiple non-detections. But the key here is that the clustering of our polarized radio detections occurred in this lower quadrant here just after orbital conjunction for the innermost planet. So normally we would expect the stochastic events should not correlate with the orbital position of the planet if they were just of stellar origin. But we're actually seeing a potential clustering of the detectability of such emissions, the polarized emissions, potentially SPI, and at these particular orbital phases. So that was the kind of really tantalizing result accumulated over the past several years. So we want to really take it a step further to understand, does that make sense? Should we expect this kind of recurrence if we actually examined the magnetic field topology of the host star? What we did was we got spiritual observations of the target and inferred the large-scale magnetic field topology using DDI. We already heard about this earlier this week. Stefano gave a nice review of it yesterday. So I'm going to show the polar maps here of the magnetic field. We see when we reconstructed that field to our best estimate, a actually large-scale dipolar field topology that is relatively strong given its low mass. The poles are around 200 Gauss. And the main key here is that both strong and a large-scale dipolar field, with the field being somewhat off the rotation axis. There's a little bit of obliquity there in the magnetic field pole. So we can take that and then extrapolate the surface field out through the stellar space to the location of the planet itself. Now, sort of visualizes the field, and in doing that, there's some closed field lines, and then the field lines extending out openly near the poles. And then this shows the rotation of that field for the radial field is what we really extrapolate as it rotates in and out. And you see that there are times where the South Pole, the North Pole will face us from our vantage point. Okay. The first thing you do is, ask the question, is extrapolation consistent with the burst densities we would expect being powered by the potential star-planet interaction? So that's what I'm showing here as a function of the assumed magnetic field of the planet itself. So there's the kink here, which is the minimum corresponding to when the planet field can push back against the stellar wind. Then as it grows, the interaction increases, and you get potential burst densities that are consistent with the detections when you get a planet field of around 10 to 20 Gauss. Okay, that may seem kind of strong for potential planets, maybe Earth-sized planets, but also we actually have no constraints on exoplanetary magnetic fields, especially for terrestrial-like planets, and really we need data to be guiding geodynamos in the future. So this is a step in that direction. And really, there are a lot of uncertainties in this type of calculation. And the fact that these detections and the modeling is right in line with kind of where we would expect is really heartening that this is really possible. And understanding that modeling a little bit better is going to lead us to pin this down more closely. Okay. So we have a field topology. The next thing we can do is consider, okay, this is the orbit of YZ It's an RV planet. So we don't quite know the 3D orientation, but assuming that the orbital angular momentum is consistent with the stellar rotation axis, we can place it in 3D space, consider how it matches up to the magnetic field. And we can map the location of the planet along the flux tube connecting the star to the planet at the rotation, at the radio detection epochs. So if we do that, what we see here is actually during all of the radio detection epochs, the foot point associated with the planet is clearly visible. And not only that, for epochs A and D, not only is the orbital phase really consistent, but the rotation phase is almost exact. And in fact, which is we examine as the synodic period, meaning that the geometry both for the orbit and the magnetic field is consistent, and we're able to see the radio emission quite clearly at both times. Time C is actually near quadrature, and this is actually really classic, what you might expect for the emission, whereas in B, you're kind of almost looking at the pole. So that one's a little interesting, but maybe is why we are able to, or why that particular pole shows a much different temporal morphology than either A, D, or C. So I want to put my conclusions up and then really kind of emphasize that the combination of radio emission and magnetic field topology is telling us something really important for understanding and evaluating potential SPI systems. We're going to take this field and push forward with modeling interaction, seeding, MHD simulations, and really following up further with radio monitoring to confirm and really nail down that this is potentially really happening. But the other thing I want to emphasize is that the geometry is so important. And there are times where the ZDI topology and the location of the planet don't coincide favorably for our observability of potential radio emissions. So even if there are observations and we've been searching for these things for quite a while, we may not be having the right observing strategies to do this well, because we actually need extended monitoring and really understanding the topology to interpret both the detections and the non-detections to be consistent for the potential SPS scenarios. So thank you.
Thanks for the great talk. You talked about the importance of the ZDI map. So, how many ZDI maps do you have? How much do you know about the stability and whether that was actually coincident with the radio detectors?
Yeah. So the question is, how many ZDI maps do we really have, and do we know how coincident they are with the radio data sets? So let's see. So there's a kind of important underlying position there in that is the ZDI map potentially evolving between epochs, right? And there's maybe a couple of years between these observations and some of the radio data sets, but not more than a couple of years, right? And the actual ZDI map is actually really well sampled in phase. So I think the map itself is pretty good from what we have, but there is a couple of years separation. So we want to understand both, and that's actually really important moving forward. What is the long-term evolution of the topologies of these fields so that we can make sure that the kind of phasing is right and accurate. But I will say that the fact that in epochs A and D, they're so coincident and we're seeing both the emissions, it's hard to think that maybe it was not stable across that time span. It's absolutely the case that we need additional observations to make sure that that is actually taking place.
Okay. Hi, I'm Julian Alvarado from Lightning Therapy. Thank you for a great talk. The answer kind of stole my question, but then I'm going to ask you another one. Can you tell us something a little bit about the intrinsic flaring of the star? Like, this is maybe due to SPI, but the star might be doing also things on its own, right?
Yeah, that's okay. So the question is, can I comment on the intrinsic flaring of a star and how that's maybe related to potential activity and other things? It's a slow rotator. There is an occasional flare in the test light curves, but I think we have to really consider the radio emission specifically. And the sort of the black arcs here indicate when we have unpolarized radio detections. We definitely saw some flaring taking place, but really we're using the coincidence in the orbit to really understand that the idea of SPI better, and that's more important, I think. But understanding the stochastic probabilities is really important, which is why we need a lot more data sets, including non-detections that say, okay, the overall rate of these kinds of events is so low that this coincidence is so unlikely unless it is actually SPI.